Hello students, welcome to AIMS India online classes. This is chemistry session. In this we are discussing about the chapter atomic structure. In this session we are going to say about the photoelectric effect and the electromagnetic spectrum. First among them is photoelectric effect. In 1887, Hedge performed a very interesting experiment in which electrons were ejected when certain metal was exposed to a beam of light. Yes, he did an experiment with some metallic objects. He took a object. We know metals will be having electrons in their valence shells. So when a metallic object is taken and he exposes a beam of light onto this metal surface, then electrons are ejected from the metal surface. This interesting experiment was observed by Hedge in 1887. What he did here, he took a metal surface, a plain metal surface. Onto this, he passed a certain light. He exposed the metal surface to a certain metal light radiation. Then, immediately, some electrons are being ejected out from this metal surface. So he called this phenomenon as photoelectric effect, which means photo, we know, photo represents light. So the electrons, the effect of ejection of electrons from metal surface on exposing to light is called photoelectric effect. And these electrons ejected are called photoelectrons. Okay. This process is also often referred to as photoemission, means emission of electrons with the light. When light strikes the metal surface, that metal releases or emits certain electrons. This is also known as photoemission. And these ejected electrons are called photoelectrons. In terms of their behavior and their properties, photoelectrons no different from the other electrons. Yes, actually, as these electrons are ejected by the effect of light, these are called photoelectrons. Even though they are called photoelectrons, there is no difference between the normal electrons, other electrons, and these electrons. They're almost all same. The prefix photo simply tells us that electrons have been ejected from a metal surface by the incidence of light. Yes, as these electrons are ejected by the incidence of light on the metal surface, these electrons are specially called photoelectrons. Other than that, there is no difference between the other electrons and these photoelectrons. Okay, this ejection of these electrons from the metal surfaces when a certain light is exposed onto this metal surface is called photoelectric effect, and these ejected electrons are called photoelectrons. Okay, next, the results observed in this experiment are the electrons are ejected from the clean metal surface as soon as the beam of light strikes the surface. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Yes, this is striking of light onto the metal surface and the ejection of electrons from metal surface both will occur simultaneously at the same time. There is no time lag between these two. Immediately, when the light strikes the metal surface, immediately electrons are ejected from it. So these two occur simultaneously at the same time. The number of electrons ejected is proportional to the intensity or brightness of the light striking the metal surface. So the number of electrons ejecting is dependent on the intensity of the light or brightness of the light. As the brightness of the light increases, more number of electrons are being ejected from the metal surface. For each metal, there is a characteristic minimum frequency below which photoelectric effect is not observed. At a frequency, the ejected electrons come out with a certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of the light used. Yes, all the metals, they want to release electrons with the same light. So each and every metal has its certain minimum energy barrier below which they cannot show this photoelectric effect. That minimum energy required to eject the electrons from metal surface is called threshold energy, and the frequency of that energy is called threshold frequency. So if we supply the energy required to eject the electrons, then only electrons are being ejected from the metal surface. So if we supply more energy than the threshold energy, then the remaining energy is converted into the form of kinetic energy of these electrons. Okay, as we give more and more energy, the kinetic energy of these electrons emitted will be more. Okay, each and every metal has a certain energy barrier below which they cannot eject electrons. So that energy barrier is called threshold energy, and the frequency of that energy is called the threshold frequency. So if the energy supplied is more than the threshold energy, then only those metals can eject electrons. If the striking photon has energy equal to h nu and the minimum energy required to eject the electrons is h nu naught, then the difference in the energy is transferred as a kinetic energy of the photoelectrons. Yes, as we told, each metal has four threshold energy. If we supply certain total energy as h nu, and the required energy to eject the electrons by the metal is h nu naught, where this nu naught representing threshold frequency, which is also this total energy is also called work function. The minimum amount of energy required to eject the electrons from the metal surface is also called work function. Then the difference between these two energies, whereas h nu is the total energy passed onto the metal surface, h nu naught is the energy required to eject the electrons. So the difference between these two energies is converted into the kinetic energy of those electrons. So when you pass an energy of h nu naught onto the metal surface, out of that h nu naught energy is utilized by the metal surface to eject these electrons out, and then the remaining energy in this h nu is converted into kinetic energy of those electrons, which are called photoelectrons. Okay, now these three can be related like this. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by the equation. See here, conservation of energy is applied here also. The total energy h nu naught is equal to energy required to eject the electrons h nu naught plus the kinetic energy of the electrons. So by using this conservation of energy principle, we can find out the kinetic energy of the ejected electrons like this. H nu naught, H nu is equal to H nu naught plus half mv square, where H nu is the total energy passed on to this metal surface, and H nu naught is the energy required to eject the electrons by the metal surface, and the remaining energy is converted into kinetic energy of that electron, where me is the mass of the electron and v is the velocity of the electron, or velocity associated with that ejected electron. So the metal which requires less amount of energy for the ejection of electrons can show this photoelectric effect very effectively. Generally, cesium is the best metal used in photoelectric cells, as it has very less ionization energy. Yes, we know the energy required for the ejection of electrons by the metal atoms is called ionization energy also, as we know. So the metals which have very low ionization energy can show this photoelectric effect very easily. Means by supplying less amount of energy only, they can eject these electrons easily. So some metals like cesium, we know these metals have very low ionization energies. So these can show photoelectric effect very effectively. Cesium is the best metal which is used frequently in photoelectric cells, as it has very low ionization energy. Let us see some solved examples based upon this kinetic energy and photoelectric effect. See the question given here. An ultraviolet radiation with a wavelength of 250 nanometers is incident on a silver foil whose work function or threshold energy is equal to 6.9 into 10 to the power of minus 19 joules. Now, what is the maximum kinetic energy of the emitted electrons? Okay, if you observe here the question, they have given the wavelength of the energy passed on to the metal surface, and then energy required by the metal atoms are the work function or threshold energy of the metal is also given. Now they're asking to find out the kinetic energy of these photoelectrons. Given here, work function of the metal or silver as 6.9 into 10 to the power of minus 19 joules, and wavelength of the radiation passed on to the metal surface, that is 250 nanometers. If we convert this into SI unit, that is meters, it becomes we know 1 nanometer is equal to 10 to the power of minus 9 meters. So when it is converted into meters, it becomes 2.5 into 10 to the power of minus 7 meters. Now we know Planck's constant H is equal to 6.625 into 10 to the power of minus 34 joule second, and speed of light, velocity of light, c is equal to 3 into 10 to the power of 8 meters per second. So by using this all, we can find out the kinetic energy of the ejected electrons or photoelectrons. Before that, let us find the energy of the incident light, energy of that UV light radiation. Because if you know the energy, we can find out kinetic energy also. So they have given the wavelength. This wavelength, by using the wavelength, we can find out energy by using the formula E is equal to hc by lambda. Wavelength lambda is given. We know h as constant and c also as constant. If we substitute these all values, we can find the energy of the incident light as 7.95 into 10 to the power of minus 19 joules. So total energy is found, and the threshold energy of the silver metal is given, and now they are asking to find out kinetic energy of the ejected electrons. Now we have total energy E is equal to threshold energy W naught or work function W naught plus kinetic energy. So in this energy we just now we found as this, and work function is given. Now we have to find out kinetic energy. This we have to find out. Let us make it subject. So kinetic energy is equal to total energy minus work function. Substitute these two values, we get energy as 1.05 into 10 to the power of minus 19 joules. So the maximum kinetic energy of the emitted electrons will be 1.05 into 10 to the power of minus 19 joules. So in this way, we can find out the kinetic energy if we know the total energy and work function or threshold energy. Okay, sometimes they may not give the energies. They may give either frequency or wavelength. By using those frequencies and wavelengths, we can find out energy. We have relations between them. If the frequency is given, energy can be calculated by the formula E is equal to h nu. Or if the wavelength is given, just like this here, we can find out the energy by using the formula E is equal to hc by lambda. So once if we find the energy and work function, if we subtract these two, we get kinetic energy. Okay, this is about photoelectric effect. Next, spectrum, electromagnetic spectrum. The light that we see from sun or from an incandescent filament lamp is a white light. Yes, a white light is composed of 7 component colors, namely violet, blue, green, yellow, orange, and red, as shown in the figure. Yes, we know the light emitted from the sun or an incandescent filament bulb. From this all, we say white light will be emitted. Actually, this white light is a component of 7 colors. Vibgyor colors. When this white light is passed through a prism, glass prism, it splits into 7 component colors as shown here, which are commonly called Vibgyor. So the splitting of this white light into its component 7 colors is known as dispersion. When we, as we told, when we pass this white light through a glass prism, it splits into 7 component colors. The splitting of white light into 7 component colors is known as dispersion. The array of 7 colors extending from red at one end and to violet at the other end, similar to rainbow colors, is called spectrum. Yes, this array of 7 colors from red to violet is called a spectrum. Atoms, molecules, or ions that have absorbed radiation are said to be excited. The radiation emitted by these substances form a spectrum. The light emitted by a sample of excited atoms is called atomic spectrum. Okay, when atoms, molecules, or ions, if they absorb radiation, then they are said to be in the excited state. What do they do? Immediately, they emit this excited, they absorbed energy immediately. That emitted energy forms a spectrum. The light emitted by a sample of excited atoms is specially called atomic spectrum. A sample of a gas contains an enormous number of atoms. Although a single atom can be in only one excited state at a time, the collection of atoms contain all possible excited states. Yes, suppose a gas is taken, it will be containing enormous number of atoms. When energy is supplied to this gas, atoms absorb energy and they come into excited state. At once an atom will be in one excited state. But as there are many atoms, all the atoms may not be in the same excited state. Some they absorb less energy and they will be in less excited state. And some atoms they absorb more energy, they may go into different excited states. Okay, the light emitted as these atoms fall into lower energy states is responsible for the spectrum. It is important to note that such a spectrum consists of bright lines on the dark background. This is called emission spectrum. Yes, when we make this energy emitted by the atoms to fall on the screen, it is observed that some bright lines will be absorbed on the dark background. So this is called emission spectrum because the spectrum is obtained by the emission of light by the atoms. So it is called emission spectrum. This emission spectrum is seems like some bright lines on the dark background. Hydrogen spectrum. Hydrogen spectrum is the simplest of all atomic spectra. When an electronic discharge is passed through hydrogen gas at low pressure, a bright light is emitted with a spectrometer and is found to comprise a series of lines of different wavelengths. Yes, when an electric discharge is passed through hydrogen gas at low pressure, a bright light is emitted with a spectrometer and is found to comprise a series of lines of different wavelengths. What does it mean? When certain amount of energy is passed onto the hydrogen gas, the atoms present in the hydrogen, they absorb this radiation. So they go into excited state. Immediately these hydrogen atoms emit this energy out. So when this emitted energy is observed through spectrometer, it is found to comprise a series of lines of different wavelengths because there are so many atoms in the hydrogen gas. So they absorb different amounts of energy. If one atom is absorbed less amount of energy, it will go to lower excited state. So this releases less amount of energy when it is coming back. Some atoms they release more energy as they absorb more energy. So in this way, the emitted energy comprise of series of lines with different wavelengths. Some of the lines are present in the visible region while the others in the ultraviolet and infrared region. Yes, these lines will be observed in the different regions. Some they will be observed in the visible region, some they will be in the ultraviolet region, and some are in the infrared regions. We can see here different lines observed in the hydrogen spectrum. Means the when energy is emitted by these hydrogen atoms, different lines are observed with the different wavelengths. Some are observed in the visible region, some are observed in the ultraviolet region, and some of the lines are observed in the infrared region also. The hydrogen spectrum consists of several series of lines named after their discoverers. Yes, these are, as we have seen, different lines are observed in different regions. So these are discovered by different scientists. So these are named with their discoverers' names. So these different series are named with the scientists who discovered those. The first of these series was discovered by the scientist Balmer in visible region. Only this series is visible to the naked eye and is named after the name scientist who discovered it as Balmer series. Okay, this is the only series which can be seen with the naked eye. Balmer series. Balmer series is obtained when excited electron is jumped from higher orbits to second orbit. Yes, when hydrogen atoms absorbing energy, those electrons will go into excited states. Different electrons will go into different excited states in the atoms. So when electron comes back, as these excited atoms are unstable, they immediately emit that energy taken. So when electrons which are excited, when they come back to the second energy level, they release certain amount of energy that forms this Balmer series. So Balmer series is obtained when an excited electron is jumped from higher orbits to second orbit. Balmer showed that the wave number of any line in the visible region can be expressed by a single empirical equation, simple empirical equation, which reads as nu bar is equal to r into 1 by 2 square minus 1 by n square centimeter inverse, where n is a number of the higher orbit from which electron jump to the second orbit. That is, n might be third, fourth, fifth, sixth, or any higher orbit. And r is a constant called Redbox constant. The value of Redbox constant for hydrogen is taken as 1.109677 centimeter inverse, or 1.09677 10 to the power of centimeter meter inverse. Sorry, meter inverse. So it is Redbox constant. Now, Balmer has given an expression to calculate the wave number of that emitted light. The formula is nu bar is equal to r into 1 by 2 square minus 1 by n square centimeter inverse, where n representing the number of the higher orbit from which electron is jumping to the second orbit, and r represents the Redbox constant, where Redbox constant value is taken as 1.09677 into 10 to the power of 5 centimeter inverse, or 10 to the power of 7 meter inverse. Okay. The wave numbers of different lines in the series are obtained by the substituting n values. Yes, if the value of n is substituted, then we get wave numbers of different lines. So n might be 3, 4, 5, or 6, any higher orbit number. So if the number of the orbit is substituted, wave number of the emitted radiation will be calculated. Next, Lyman observed some more spectral lines in the hydrogen emission in ultraviolet region. So it is called Lyman series. Yes, Lyman observed some more series of lines in ultraviolet region, as he discovered those with the name given Lyman Series. Pascal, Brocket, and Pfund observed separately three different series of lines in the infrared region. So they are named with their names as Pascal series, Brocket series, and Pfund series. These three series are found in infrared region. Out of this, Pascal series is said to be nearer infrared region, Bracket series is said to be infrared region, and Pfund series is said to be in far infrared region. Okay, different spectral lines of hydrogen emission are shown here. You can observe Lyman series, Balmer series, Pascal series, Bracket series, and Pfund series. These all are obtained when excited electrons falls into different energy levels. When electrons from the higher orbits jumps into first orbit, comes back to first orbit, then the energy emitted will form a series called Lyman series. When electron jumps from higher orbits to second orbit, then the emitted radiation forms a series of lines called Balmer series. In the same way, fast and rocket P-fund are formed when electron jumps from higher orbits to third, fourth, fifth orbits respectively. Okay, next. Rydberg gave a more general expression which can be applied to all the series of hydrogen spectrum. This expression is called Rydberg's formula. Actually, Balmer formula is only for the calculation of energy emitted by the radiation when electron jumps from to higher orbit to second orbit. But it is generalized. It is given a generalized expression for the calculating of for the uh, calculation of energy in all the series. That is called Redbox formula. It is given by the formula nu bar is equal to 1 by lambda into 1 by lambda, that is equal to R into 1 by n1 square minus 1 by n2 square centimeter inverse, where n1 and n2 are whole numbers, where n2 is always greater than n1. n1 is the number of the lower orbit to which electron jumped, and n2 is number of the higher orbit from which electron is jumped. Okay, n1 and n2 are the numbers of the orbits, where n1 represents the lower orbit to which electron jumped, n2 represents the higher orbit from which electron is jumping, and r we know as it is a Rydberg constant. For one electron species like hydrogen, He plus, Li plus 2, Be plus 3. Already for hydrogen it is the expression from all the orbits. And there are some more one electron species like helium plus, Li plus 2 and beryllium plus 3. The value of R is taken as 0.109677 into Z square centimeter inverse, where this Z is representing the atomic number of the species. Now, the wave number for any single electron species like He plus, Li plus 2, Be3 plus can be calculated by using the formula nu bar is equal to Z square RH into 1 by n1 square minus 1 by n2 square centimeter inverse, where Z is the atomic number of that single electron species and R is the Rydberg constant. By using this, wave number can be calculated for single electron species. Okay. See here different spectral lines in the hydrogen spectrum are shown. What we said, Lyman series obtained when electrons jumps from higher orbit to first orbit. The higher orbit might be any more than two. It might be second, third, fourth, or anything. If Balmer series is obtained when electron jumps from higher orbits to second orbit. Okay, you can see here. So n1 in the place of n1 for different series, different numbers are used because n1 is different for different. Lyman series, n1 becomes 1. If it is P1 series, n1 becomes 5. So in this way, wave number can be calculated by using this formula for the emitted radiation. So if the wave number is calculated, energy also can be calculated because we have relation between energy and free wave number. Okay, this is about spectrum and hydrogen spectrum. Thank you for watching our video. Please subscribe our YouTube channel, that is AIMS Today, for latest updates on recorded videos. Thank you.